My name is Anjani Kumar. I'm the Vice President of Engineering Solutions and Marketing at CMG. I'll be the moderator for today's session. I'm pleased to introduce Jeremy Galban, a reservoir simulation engineer at CMG, who will be presenting today's webinar. Jeremy has more than 8 years of industry experience, and he specializes in recovery of oil and gas from unconventional reservoirs. He has both field and simulation optimization experience in hydraulically fractured wells. Prior to joining CMG, probably Jeremy 4.5 years ago, he worked in field operations in the hydraulic fracturing of shale reservoirs in the US. Jeremy holds a Bachelor's of Science degree in Petroleum Engineering from Colorado School of Mines. So he'll be going through some of the basics of simulation workflow using CMG tools. At this time, I would like to inform you that there will be a question and answer session at the end of the presentation. However, you may submit your questions at any time using the chat window on your screen. We will also post the recorded version of the presentation on our website within the next 24 hours. You'll have to use in your CMGL login and the password to access the material. Over to you, Jeremy.
Thank you, Anjani. Hello, and thank you for tuning in on today's webinar. Today we'll be going through various methods of setting up your simulation model, as well as using CMOST to history match your simulation to any field data that you have. We'll also be taking a look at how to implement an optimization study on your match model to maximize the NPV of your field. CMG has been around for over 40 years. We started as a research foundation at the University of Calgary in 1978. A couple years later, we released our first simulator IMEX, followed by GEM and STARS. In the 1990s, we released WinProp, our fluid phase behavior modeling simulator, and Builder-in Results, which are our pre- and post-processor visualization software. As technology advanced, we continue to work hard and develop these technologies into our software, as evident of our hydraulic fracture modeling in 2008, and CMOST AI, which is our semi-automated history match and optimization tool. As of 2016, 100% of the top 20 Canadian heavy oil producers use CMG in their projects. CMG is the simulation market leader and experts in EOR and advanced recovery methods. Specifically, we excel in unconventional resources such as tight oil and gas, compositional models such as CO2, nitrogen, and solvent injection, thermal processes such as SAGD, CSS, steam flooding and combustion, chemical models in the form of ASP flooding, foam, and gels, and models with geochemistry such as in low salinity water injection. CMG software is used all over the world. We have over 600 different customers in 60 countries. We have 7 offices across the globe and an additional 9 different locations with CMG agents, which are represented here on the map. Here's a list of our products. Today we'll be exploring the different tools available to you within Builder, which is our visualization and pre-processing software. You'll find that Builder has a lot of built-in correlations and import functionalities to populate reservoir grids and properties, create fluid and relative permeability models, as well as import historical field data to assist in history matching your simulation. Once we have imported all of our data, we can run our model using one of our simulators and view the results in either graph or 3-dimensional format using results. To aid in history matching and optimization, we can also implement the use of CMOST AI to get faster results and better understand our simulation model. So today we will go through various methods of importing your data to create your model, which we will then history match and use in the forecast optimization of our field. The example model I'll be using for this webinar is a tight oil reservoir, but all the wizards and methods I'll be showing you today can be applied to any of your models and EOR processes. And with that, I'll go ahead and jump straight into Builder and show you the various tools within it and how to use those tools to better understand your model and your projects. Now, I've already loaded my model through the use of a rescue file, but there are a few different other ways you can go about this as well. One of the ways would be to import a surface map by going into File, Open Map File. And you would choose from any of the specific map types available to you here and choose the units for your map. And once you've loaded that in, you'd be able to see the contours on the top of your map. You would go into specify property and assign that surface map to the grid tops. If you have additional surface maps, such as differences in layers, you'd be able to create multiple layers and assign those layers to your surface map. Additionally, you can populate the properties of your reservoir through geostatistics. To access the geostatistics, you would go into Reservoir, into the Geostatistics tab here. As you can see, I've already loaded in some well logs for wells 1, 2, and 3, along with the porosity, which can be seen here in the right column. Now, this porosity is going to act along the trajectory of each one of these wells. And when I go over to the methods, I would choose from either of the Kriging or Gaussian geostatistical methods, set the settings of my geostatistics, and click on Run. Builder will then go through and populate the well log properties you've loaded throughout the entire model. Properties such as permeability, porosity, water saturation, and even formation tops can be populated using the geostatistics wizard inside of Builder. Alternatively, if your model is structurally simple, you can also create a box model by going into Reservoir, create grid, and Cartesian. You would then choose the dimensions of your grid blocks and a simple box model will be made for you. I mentioned earlier that I already loaded in a rescue file for my model. To do this, I went to Reservoir, Rescue, Open Rescue File. And when I open this rescue file, Builder will go in and it will scan for any sort of reservoir properties, any sort of structure inside of my model, as well as any wells, which can be shown here in the background. Now, Builder does a very good job of looking into the rescue file, looking at the name of the properties inside of your rescue file and assigning it to the CMG, the associated CMG property. So in this particular case, it was able to find my perm I, J, and K, along with porosity and any pinch out and null blocks. If for some reason these properties were named something else and Builder wasn't able to identify them, you would go through here in the top left pane, take that property and match it to the corresponding CMG property here on the right side and choose add selected map or add to selected mapping. Once you've loaded, or as you can see, I've loaded in my model already. Looking at the porosity of my model, you can see that I have a porosity ranging from about 3 to 9%. And if I look at the permeability, I can also see that the permeability of my matrix blocks range from between 5 to 17 microdarcies. Once I've loaded in my model, the next step would be to import my PVT data. So if I go under components and click to open up the PVT data, I can see that I've already loaded this. Now, if you already have pre-existing PVT data from any sort of lab experiments that are in this sort of pressure format, you'd be able to go ahead and copy and paste that information directly into Builder. Additionally, if you had limited data, you can also choose to generate PVT using correlations by going into tools and generating using those correlations. In this particular case, I've already imported in my data for a 30 API fluid with a gas gravity of 0.92 at a temperature of 240 degrees and a bubble point pressure of 2025 PSI. I would then go and choose the specific correlation that I wanted to use to populate my oil and gas properties. And when I click apply, this table here in this window would populate for me, and you can see that it would have populated the relationship of R sub S, B sub O, B sub G, and the viscosity of my oil and gas, all according to pressure. Additionally, you can create and import a matched WinProp fluid model if you have the data for your fluid. WinProp is our phase behavior modeling software, which is used to match lab data, and the properties of the fluid can then be imported into any of our simulators by going into components and import WinProp generated model. Additionally, there is an advanced process wizard that's available to you within GEM and STARS. And just to demonstrate that, I'll go ahead and open up a STARS dataset, which you can see here in the background. Just to show you how to utilize this process wizard, I'm just going to open up this STARS dataset. Even though we won't actually be modeling these advanced processes today, this is just to show you how this advanced wizard works and how you can access this. To access the advanced process wizard, I would go into Components, Process Wizard, and if I open up the drop-down box, you can see that there's a variety of advanced processes that I can access. Now in the STARS model, I can access a foamy oil model, combustion model, ASP or foam injection model, low salinity water injection, or an asphaltene precipitation model. Just to show you how this wizard works, I'll go ahead and choose the alkaline surfactant foam and polymer injection model. And when I click next, I can then also have the option of just bringing in a polymer flood, just doing an alkaline surfactant, or in this case, I will choose to add all three components for my alkaline surfactant and my polymer flood. When I choose to add all three components for my ASP, you can see I have options on how I want to specify the properties of my polymer, such as defining a polymer function for my viscosity according to salinity, as well as a polymer half-life. I also have options of defining how my relative permeability changes in the presence of surfactants, as well as any adsorption for my surfactants. When I click next, I also have the option of defining any sort of geochemistry type calculations that I want to input into my STARS model. Now I just want to go back into the IMAX dataset. And once you have imported in your PVT data, the next thing you'd want to do is import the relative permeability by going into rock fluid and double clicking on your rock fluid types. Now, if you have pre-existing data for your relative permeability, possibly from a nearby well or somewhere else out in your field, you can go in, copy and paste that information specifically for that relative permeability here. Another option that you have within Builder is to populate your relative permeability according to the Corey equations and any sort of endpoints that you might know of. So to do this, I will go to Tools and Generate Tables using Correlations. And as you can see here, I've already input a conate and critical water saturation of 25%, as well as any irreducible and residual oil saturations for my curves. And when I click OK, you can see in the background that these relative permeability curves would get populated for you. One additional function inside Builder that would specifically help with your history matching is you are able to also go in and alter these relative permeabilities manually as so. So for this particular case, what I'm doing is I'm taking the water relative permeability curve, which is here in red. And if I'm trying to do a history match and I'm seeing in my results that my water production is just a little bit too high and I wanted to kind of manually alter this curve, I can do that using this method and altering my water relative permeability curve rather than going in and actually typing in exactly what that value should be here. Now, whenever you alter a curve like this, or if you import any sort of relative permeability data that might not necessarily be smooth, Builder also has a function inside of it to help you smoothen that relative permeability as well. This can be accessed by going to Tools, Smooth Table, and you would choose the type of smoothing that you'd like to do for your relative permeability. In this case, I'll choose the default smoothing for all properties. And you can see here in the background that there's this green curve that's kind of overlaying my, my original water relative permeability curve. Now this green curve is going to be that smoothing that we're going to add to our relative permeability. And when I click OK, you can see that my water relative permeability curve is a lot smoother. And this can actually help tremendously in terms of numerical tuning and data set numerical stability. Additionally, there's an option to apply endpoint scaling into your relative permeability curves. To access the endpoint scaling, I would go into Tools, Curve Scaling. And if for whatever reason I wanted to scale my curves back for my critical water saturation as well as my connate water saturation, I'll be moving that from 25% to 30%. I'll click on the Scale Curves button, and as you can see here in the background, the original water and oil relative permeabilities were the blue and the red, and I've scaled these curves to move the critical water saturation from 25% to 30%, as well as the connate water saturation from 25 to 30%. And when I click OK, you should see that this relative permeability has been scaled for me. And I'll just move that back. For the initial condition section, this section is going to control how your model is initialized. If I double click on initial conditions, you can see that I'm going to specify an original reservoir pressure of 2600 psi at a reservoir depth of 3,770 feet. I've also defined my water oil contact and my gas oil contact of my field. Just by specifying the reservoir pressure at a specific depth, the simulator knows exactly what fluids are going to be in my system, as well as the densities associated with it. So the pressure of my entire reservoir will be populated for me during the initialization of my model. There is an additional geomechanics option that's available in all of our simulators, IMAX-GEM and STARS. We do offer high fidelity geomechanics modeling, which implements finite element analysis in your grid that simulates stress and strain in your reservoir rock. This high fidelity advanced geomechanics modeling can also be used to identify any splitting of grid nodes, such as in the cases of fracture initiation and propagation of hydraulic fractures. We also offer low fidelity geomechanics modeling, such as simply using dilation and compaction tables to characterize the porosity and permeability of your rock according to specific pressure changes. Now, I mentioned earlier that I've already imported in my my wells through rescue format. If you didn't have wells inside of your rescue format, there are a few other different ways that you can import your wells within Builder. One of the easiest ways of doing this is going into the wells and recurrent section, well trajectories, and choosing to import those well trajectories. Typically, the well trajectories are in some sort of XYZ format. And so with that XYZ format, it would define the shape of your wells. And from there, you would go in and choose the trajectory perforation intervals option, which will then specify exactly where the perforations are inside of your wells. Now, I showed you earlier that we're using a tight oil model for this particular example. So now I'd like to show you how to implement hydraulic fractures into your model. There are 3 ways to implement hydraulic fractures using Builder, and typically you'd use one of these 3 ways in your model. But as an example, I will show you the various methods using the 3 wells I've already loaded. So the first way of importing hydraulic fractures would be to go into the wells and recurrent section and choose hydraulic fracturing. So for well 1, I'll show you how to create a planar fracture. The first step in creating a planar fracture would be to go to the template section and choose to create a new template by clicking on the green plus sign. And in this particular case, I've already created a template called planar template. You would define the intrinsic fracture width of your planar fracture. In this case, I'm going to define it as 0.005 feet, which is roughly about 1.5 millimeters. And I'm also going to define my intrinsic permeability of my fracture as of my hydraulic fracture as 15,000 millidarcies, as well as include a tip permeability of 2,000 millidarcies. And now the tip permeability is going to be the permeability obviously at the tips, and a linear gradient will be applied throughout the length of that fracture. Secondly, I'm going to define the direction of my hydraulic fracture, which will be in the I direction. And I'll go ahead and apply a bi-wing half length of 300 feet. To define the height, I'm going to describe the fracture as going 4 layers above my perforation, as well as 4 layers below my perforation. Once I've created a fracture template, I'll be able to go in, choose well 1 and the date at which the well was fractured, choose new planar fracture stage, and I'm going to choose that planar fracture template that I've created in the previous step. I'll choose to perforate all layers, but I also want to give a minimum fracture spacing of 300 feet. When I click apply, you can see that in the background, all of my 10 hydraulic fractures were created for well 1.
So Jeremy, we can actually, what you're saying is we can create different types of templates depending on the frac jobs that you have done in the field, and basically apply to any of the stages and any of the wells really easily using this wizard.
Yes, absolutely. And it's not just limited to having the one planar fracture template, as you mentioned. Depending on the type of stages and how you want to apply your strategy on how you want to frac your well, you can make specific templates for those strategies and easily apply them to any stage in any well. All right. So I showed you how to do the planar fracture template there. The second option that we have would be to use data coming from a hydraulic fracture wizard. And what I'm doing here is I'm just manipulating the 3D view of my builder to take out any of the low permeability matrix blocks to show you exactly what we did in that step for well 1 there. Now, if I go back into my hydraulic fracturing tab, I also have the option of bringing in importing a fracture stage, and this could be data coming from any sort of hydraulic fracture simulator. So in this case, I'll choose import fracture stage. I will load in my data, which is coming from Excel. And as you can see in this particular example, I've loaded in that data from a hydraulic fracture simulator, and it was automatically made for me here in the background. And if I go back to the previous view that I showed you earlier, and again, I just want to filter out the low permeability grid blocks so I can show you. I can see that in well number 2, I've brought in that planar fracture template and the conductivities of those fractures, which can be seen here in the background.
So just to let everybody know that we have partnered with major frac designing and hydraulic fracture simulator companies where we have standardized the format for importing hydraulic fracture data from third-party hydraulic fracture simulators. And as you can see here, that we can actually import the actual frac design from the third-party hydraulic fracture software, including the fracture conductivities and half lengths and things like that. So the wizard, hydraulic fracture wizard, actually makes the whole import process really easy and simple.
And lastly, I showed you how to do the planar fracture template and also importing the fractures using a hydraulic fracture simulator. Lastly, we can also import microseismic data into our model and then create the complex fracture network according to the microseismic events that we're finding inside our data. To import your microseismic data, you would go into Tools, Microseismic Data Manager, and you would click the import button to go ahead and import that data. I've already imported microseismic data for my well number 3, which you can kind of see here in the background. We can also animate the hydraulic or the microseismic data. So if I click on the play button there, you can see that we have the microseismic events. In this particular case, it's going to be the moment magnitude of that microseismic data. And if I choose to stop the animation, what I can do is I can go back into the wells and recurrent section, click on hydraulic fracturing, and now I'm going to apply a complex fracture according to when we see those microseismic events. So what I'll do is I will go into well number 3, click on the date that the well was hydraulically fractured, and I will click on New Complex Fracture Stage. Since I've loaded my microseismic data, there's an option at the very top that says Use Microseismic Data. I'll go ahead and click on that. And what I want to do is I want to bring in stage 10 for well number 3. So the microseismic data is going to be read for stage 10, well number 3, as you can see down here in the bottom. Builder goes in, finds out exactly where those microseismic events are, and highlights those grid blocks where I'm finding those events. And so if I click Add Selected Blocks from View and click Apply, I've now selected those grid blocks, and the last step in assigning these fractures to my model would be to define the fracture properties. So in this case, I'll define a complex fracture width of 0.005 feet, intrinsic permeability of 15,000 millidarcies, and I'll click Apply. And when I click Apply, you can see here down at the very bottom that we have created the hydraulic fractures for stage 10 in well number 3. And you can see the microseismic events in the blue dots here, as well as the hydraulic fracture, which is represented in red. Now, I've already imported in my hydraulic fractures for my well. The last step for creating my model is going to be to import my production data for my field. Now, when I import the production data for my field, this is going to help. It's going to help a lot when doing my history matching of my field. To do this, I would go into Wells and Recurrent, import production data. As you can see, I've already loaded in my file. And once I've set up exactly how I need Builder to read my file, you can see that I've loaded in data for wells 1, 2, and 3. And I've also I'm also bringing in my oil rate, gas rate, and my well bottom hole pressure on a monthly basis. When I click Next, I also have the option of assigning my oil rate as my main operating constraints for my well, again, which are going to be on a monthly basis. So once we've imported our historical data, all we need to do is submit the data set to the simulator, which I've already done. So let's take a look at the results. Now I've already loaded the results into results as well as the field history files according to the data set that we just ran. If I look at the oil rate match, you can see that I get a perfect match on my oil rate. Again, this was because we've assigned those oil rate constraints as our main operating constraints for our wells. So in wells 1, 2, and 3, looks like we get a perfect match on our oil rate. Again, it was because we assigned those oil rate constraints to our wells. If I look at the gas rate for well 1, I can see that my gas rate is under predicting what our historical constraint or what our historical file is saying. The simulator data is the solid red line, and then field historical data by default always comes in as these hollow circles. So as you can see, we are underestimating our gas rate for well 1. We're also underestimating our gas rate for wells 2 and 3 as well. If I look at my well bottom hole pressure, again, the simulator data is going to be that solid line, and the field history data is going to be those hollow circles. And it looks like we are overestimating our well bottom hole pressure for wells 2 and 3. Now, since we don't have a good match in our model compared to the field data, what we can do is go back into our model, change some of the uncertain parameters of our model, such as our relative permeability or our hydraulic fracture properties. Once we alter some of those values, we would rerun our simulation, load the results, and hopefully those changes we made would get us closer to matching the gas rates as well as the well bottom hole pressure in this particular case. We would do this manually for as many times as we needed to get a good history match, or instead what we can do is implement the use of CMOST AI to run in the background and see if we can use the machine learning algorithms to find a history match model for us. So I mentioned CMOST AI before. So what is CMOST AI? CMOST AI is CMG software with built-in machine learning that works in conjunction with IMAX, GEM, or STARS to help you understand your model through sensitivity analysis, or you can also improve the quality of your studies through history matching, optimization, and uncertainty analysis. So what I've done is I've loaded in the data set and the results, as well as the field historical data, into a CMOST study that we're going to be using for a history match. As you can see, again, this is going to be the oil rates. We get a perfect match on our oil rate for wells 1, 2, and 3 as compared to the field historical data. And with our gas rates, we underestimate that according to the field and overestimate our well bottom hole pressure according to that field data as well. So the first step in setting up a CMOST study for a history match is to go into the Parameters tab under the Parameterization section. Now you can see here that I've already set up some parameters inside of CMOST that are specifically with the hydraulic fracture properties. In this particular case, I've set up my frac perm, half length, my frac perm of the tips of my fracture, all as parameters. Now, there are a few different ways to import parameters. One of those ways to import a parameter very easily into CMOST would be to click on this builder icon here on the right side. And what that will do is it'll open up a CMOST definition box that works very closely with Builder and allows you to easily set those parameters for your CMOST study. For our particular case, I wanted to set parameters for my hydraulic fractures. So what I would do is expand the hydraulic fracture section. And as you can see, I've already set up a parameter for my intrinsic frac perm as well as my intrinsic tip permeability, which you can see here. If I wanted to set a parameter for my intrinsic fracture width, I would simply highlight this fracture width value here, click add, and it would show up here at the top. Now, this isn't just limited to setting hydraulic fracture properties as parameters, as you can also do the same thing with any of your reservoir properties. So if I expand the reservoir section, I can also change my porosity and permeability arrays. And the reason why you do this is if you had any sort of uncertainty in these values, and it would change these values accordingly to see if it helps you get a better history match. Additionally, if you also had uncertain parameters in your component section, which is your PVT, or your relative permeability, you can alter those as well. And in the case of optimization, you'd also be able to go into the wells and recurrent section. And if I wanted to, say, play around with the constraints of my well to see what my best operating strategy is, in this case, I can alter my surface oil rate as well as my well bottom hole pressure, operating pressure. And if you wanted to do a study playing around with the well spacing to see what the most optimal case would be, you can also go into the wells and recurrent section and also set parameters for the completion locations. Once you've set all your parameters inside of this window, as you can see here in the top, you would click on Save Changes, and Builder would go in and it would apply those CMOST definitions to a .cmm file, which is your CMOST master dataset file, which will then be read by CMOST. There's an additional way of adding in CMOST parameters through the use of the cEdit button. cEdit is CMG's text software, text-based software. The way you would do this is you would click on the cEdit button and you'd be able to see your data set inside of text. And for instance, if I wanted to change a certain permeability value inside of text, I could simply highlight the value that I'd want to change, right click, and I would choose to create the parameter. So as you can see, I've set 5 specific fracture properties. One's going to be my intrinsic frac permeability, and I'm going to range my intrinsic frac permeability from 5,000 to 30,000 millidarcies. If I look at my half length, I'm also setting this as a parameter and allowing CMOST to range my half length from 120 feet up to 400 feet.
So Jeremy, basically what you're saying is when you're using cedit, you don't need to remember any of the syntax for creating the parameters. You just select those variables that you want to actually convert it into a CMOST history matching parameter, and then cedit will just automatically create those keywords in the CMM file, and CMOST should be able to read those variables, right?
Yes, you are correct. So if you were to open cedit and create something as a parameter, so for instance, if I want to set my my compressibility of my formation as a parameter because I might be uncertain about it, I would choose that value, select create parameter, and if in this particular case I want to set the compressibility of my formation as a parameter, I would click OK. And cedit knows exactly what the CMOST syntax keyword should be to set my rock compressibility as that parameter.
And the compressibility is a variable parameter that you will vary inside CMOST, right?
Exactly.
All right.
And so at this particular, or in this particular case, I would allow CMOST to play around with a range that I've specified for my compressibility, and CMOST would go in and see how that compressibility changes and how it affects my results.
Great.
So once you've set your parameters, the next step would be to set the objective function. Since we are doing a history match, I would go into the history match quality tab here, and typically any sort of field data that you have should go inside of this tab. This is how we're going to define how that history match quality is calculated. So here you can see that I've loaded the gas rate for my well because that is something that we're trying to history match, as well as the bottom hole pressure. Now we already got a good history match on our oil rate, but I went ahead and included that oil rate and the field history files for that oil rate inside of our history match quality, just to make sure that that is still accounted for when CMOST runs the simulations and when it does the calculations for my history match quality. And the last step would be to go into the engine settings under Control Center. Here, we know that we want to calculate the global history match error, and we also want to make sure that we define the search direction to be minimized. The lower the global history match error, the better. Essentially, if you had a 0 global history match error, it means you have a perfect history match of your model. So I'll choose minimize there. The study type obviously is going to be history matching, and then I'm also going to choose the specific engine that I'd like to run my CMOST simulation on. Now the engines are all different types of available machine learning algorithms and AI built within CMOST. If you'd like to learn more specifically about these engines and how they work and how CMOST uses these algorithms, we do offer advanced CMOST courses in unconventional as well as thermal applications, specifically using CMOST. Another helpful option available is the customization of the schedulers within CMOST and how CMOST is going to use these resources to run your simulation. In this particular case, I've chosen to run a max number of concurrent jobs of 15 over my network. And you can also go in and choose to run some jobs on your local machines as well. And this would be to help maximize your resource efficiency. Additionally, we do offer cloud-based services as well. So if you have that option activated and available to you, you'd be able to submit your CMOST simulation to either a Microsoft or Amazon cloud-based service. Once you've chosen all of your options, simply go to the Control Center tab, hit the play button to run your study. Here. CMOST will run in the background and automatically submit your simulation runs with different combinations of the parameters you've specified, while also looking for the best history match. I've already ran this particular study, and it looks like it automatically ran about 360 different simulations. As you can see here in the chart, the first 70 or so cases had a very wide range in results, and in turn gave very large history match errors. The machine learning engine uses this information to get a quick estimate on how your selected parameters affected the results. Once it has a good estimate, the algorithm uses this information to converge to a solution which is the lowest history match error it can find. We can see here that our best case is in red, with a history match error of about 7.4%. And if I go into the results and analysis tab, I'll be able to see the results and any of the simulations that CMOST ran. The base case, the original file that we ran is our base case, which is in the solid black line. Our red case is our most optimal result, which I showed you in that previous step. And the teal lines in the background are any other runs that CMOST made for us. So in this case, we can see that we do have a fairly decent match on our gas rate for well 1. As expected, our oil rate does match very well. It looks like our well bottom hole pressure for well 1 matches a lot better. Remember in that first step, I showed you that the original model was vastly overestimating what our well bottom hole pressure should be. And our newly matched model looks like it does a pretty good job of matching that well bottom hole pressure. And I just want to go in and double check that wells 2, 3, 2 and 3 matches well. And so it looks like my well bottom hole pressure for wells 2 and 3 has a very good match. Now that we have this history match, we can rerun this model with our current operating strategies and get an accurate forecast of what we can expect for the rest of the life of these wells. Another option that we have is using CMOST to set those operating constraints as parameters and let the CMOST algorithms find the most optimal strategy for us. So what I've done is I brought in our best matched model into Builder, and I've set this model up to go on a 25-year forecast, running a huff and puff simulation to see if I can further optimize my field. If you're not familiar with the huff and puff process, the way it works is that I will inject CO2 into my wells, let that CO2 soak and dissolve into the oil to allow it to produce out of the formation a bit easier. Typically, this is set up as a cyclic process, so I'll show you how I've implemented that in my model. Also, since this process requires CO2, what I have done is I've converted my IMEX model into a GEM data set already, but to do that, you would go into your IMEX model, choose Convert Simulator Data Type, and then there would be an option there to convert it over into either a GEM or a STARS data set. Since I'm already working with a GEM data set, that option isn't available. But it would be available starting with an IMEX data set. So now that I've converted my IMEX data set into a GEM model, all I need to do is go in and make corresponding injection wells for my original producers. I've extended the life of my simulation for an extra 25 years. And I've gone into my group section, assigned those wells to a group so that I can apply my, my group cycling option. Now in Huff and Puff, there are going to be 3 specific cycle parts. And here we can see that I've defined my 3 different cycle parts as evident of values 1, 2, and 3, which you can see here at the top. Value 1 is going to be represented by my injection cycle. So during injection, I've set an original value of 320,000 cubic feet per day for all of my injection wells. So I'll be injecting at a max 320,000 cubic feet a day of CO2 just for this value 1, which is my injection process. I've also defined a max cycle part duration, and this is going to be the length of my injection cycle in terms of days. I've also included a value for my minimum injection rate for cycle switching. So at any point during the simulation, I'm not able to establish any sort of injection. What will happen is the simulator will go in and say, okay, well, stop the injection process and move straight to the soak process, which is the value 2 here. Now during soaking, I'm not going to have any sort of production or injection, so I haven't defined anything or any of those values. But I am going to set an original value of 7 days for my soak cycle. And lastly, once that CO2 is able to soak into the oil, I'm going to include a production cycle. For the production cycle, I've specified an original max oil rate of 1,500 barrels per day. with a production cycle of 180 days. And again, if at any point I'm not able to get any sort of production from my wells, I've applied a minimum oil rate for cycle switching, and it'll move straight back into value 1, which is the injection period. So I've ran this data set, and what I want to do is run an optimization study on this data set. So I've ran my data set, imported all of the values, or imported the data into a optimization study in CMOST. And I've come to the parameters tab, which you can see here. Now, in the parameters tab in the optimization process, what we want to do is we can only optimize based on operating conditions that we control. So we've already matched our hydraulic fracture parameters, and so in that particular case, I'm not going to change any of those values, but now I'm going to change operating parameters such as my injection time. If you remember, the original value for my injection time was 60 days, and so in this case, I'm going to play around with ranges between 20 and 80 days for my injection time. For my production time, my original value was 180 days. I will play around with specific types of production times ranging from 120 to 240. And the soak time I'll range between 2 and 14 days. I'm also going to set parameters based on my max gas injection rates, as well as my minimum oil and gas rates for cycle switching. Now, instead of setting a history match, what I want to do is optimize based on the net present value. And so if I go into the net present values tab, I've created a net present value calculation labeled NPV Huff and Puff, as you can see here. And I'm going to define my net present value of my Huff and Puff as having some sort of value for any of my produced oil. So in this case, I've applied a $65 per barrel for my oil rates. I also want to include any water disposal costs. And so here I've specified 50 cents per barrel of water that I will be producing. I've also included a yearly discount rate of 10% for all of my variables inside of my NPV. My cost for injecting CO2 is going to be about $2.25 per 1,000 cubic feet. So I've included that cost as well as any pump costs for my oil getting it up to surface. And once I run this, or once I've completed the net present value calculations for my optimization study, I do want to go back into the engine settings. I want to make sure that the study type I'm using is the optimization process. Set the global objective function as that new NPV calculation I've specified. And I do want to make sure that I change the search direction to maximize instead of minimize. If you remember in the previous step for the history match error, we wanted to minimize our history match error as much as we can. In the optimization case, we want to maximize our net present value. I've already ran this CMOST study. You can see here in black that my base case gave a field NPV, and so this NPV is present day, obviously, a field NPV of about $4 million. Once I've allowed CMOST to run the simulation or run the study, it's going to vary all of the parameters we specified in the previous step, and it's going to calculate exactly what the net present value is according to how those parameters are used in the simulation. The engine will run, it'll take the information that it's calculating for this NPV and how those parameters are affecting your net present value. And as you can see here, in our most optimal case, we can see that we get a net present value of almost $5.5 million instead of the base case of the $4 million. And so by running the CMOST study, we've essentially improved our net present value by about 37%, somewhere around there. So as you can see here in red, this is our most optimal case, which is experiment number 149. And so if I go into the experiments table and I scroll down to experiment 149, I can also see exactly what values of those parameters CMOST chose for me to give me the most optimal result. So if I scroll over and highlight case 149, I can see that in my most optimal case, my injection time for my cycle switching was 20 days, the soak time was 3 days, and my production time was 240 days. I've also included the min and max oil and gas production for my cycle switching, as well as my my max gas injection rate.
Also at this time, just for the benefit of the users, like to let you guys know that from the 2018 version of CMOS, you can actually submit all these optimization or history matching jobs directly to the cloud, whether it's Amazon AWS or Microsoft Azure. It lets you directly submit all these jobs onto the public cloud as well.
And lastly, I do want to go into my optimization case, and I do want to see exactly what my results look like. And so in this case, I'm looking at my cumulative oil for my huff and puff scenario. The base case is here in black, and it does look like in my most optimal case, it does give me the most oil production as well, which you can see here. So in conclusion, CMG can be very easy to use. We have multiple methods and wizards available within Builder to help import your data. In cases of geomodels, PBT, or relative permeability, when your data is limited, we also have built-in correlations and geostatistics to help you build your model. Once you have your model set up, use CMOST AI to aid in the history matching. And once you have your history match model, you can forecast that model to optimize the net present value of your field.
Thank you, Jeremy. So as you can see, there are a lot of wizards available in Builder that helps you through a guided task on helping you create and achieve complex tasks and help you build these models quite easily. And then in conjunction with CMOS, the entire workflow is pretty streamlined, whether it's from sensitivity analysis all the way to optimization and uncertainty analysis as well. So at this time, we have several questions on the screen, so we will take those questions one by one. Just for privacy reasons, I will not be taking the name of the attendee that is asking the questions, but I'll read the questions so that the relevant person can recognize their question. So the first question is, can you please elaborate on the asphaltene precipitation model in stars? Is that a recent capability that is added? The asphaltene precipitation model has been in stars for several years, actually. It's a pretty comprehensive model, and there are several SPE publications on that particular model. We do have training materials as well, which covers the asphaltene precipitation model quite in detail. I don't think I'll do justice in explaining that here in just a few minutes. So what I'll do is I have the contact details of this attendee, and I will be sending the question or the material to the individual offline. The next question is, can the hydraulic fracture wizard be used to simulate a non-sealing fault? Is there another way to do this other than the dual permeability or porosity model? And I recognize the name. I mean, this one is a long-term user of CMG. So basically, there are several ways in which you can actually model a non-sealing fault. The traditional way is define the fault and you can model the transmissibility. But if the transmissibility or conductivity of the fault changes with time because of pressure or stress changes, then there are multiple ways you can actually do it. You can actually use the full geomechanics model, where you can use one of our geomechanics module to actually change the conductivity of the sealing fault or the non-sealing fault. You can also use the Barton-Bandis method as well, that is pressure or stress dependent. You can also use the hydraulic fracture type of gridding, where you can use a compaction dilation tables where the conductivity of the fault is a function of pressure change as well. So there are several ways that you can model it, and you can definitely use the LSLRDK grid that we use for hydraulic fracture to capture the conductivity variation with pressure. So the next question is the question is back to history match. How much your frac properties change from base case to the optimum matched case?
Let's see, I will bring that back up here. And so if I go to the parameter section inside of my CMOS dataset, you can see that I had default values here. So my frac perms and my tip would be from 30,000 to 2,000. Half length is 300, and then my layers up and layers down were 4 or 5, and that would be the fracture height. And so very easily I can go in and find it. In my most optimal case, I can see that it was experiment number 276. So if I go back to my experiments table, go to 276 and scroll over, I can see that this is my most optimal case. And so my original value for my frac perm was 30,000. My original tip permeability was 2,000. My new half length is going to be 204. My original value was 300. And then layers up and layers down, I think those were each 4. I think 4 each.
Yeah.
Okay.
Yeah.
So as you can see, it didn't change too much. We just needed to alter these fracture properties a little bit to help get that match.
Okay. The next question is, how would changing the AI algorithm help in either history matching or optimization? As Jeremy showed, there are several AI and machine learning algorithms inside CMOS. Now, depending on the type of history match you want, whether you want a single history match or you want multiple history match which meets your acceptable criteria, and depending on which engine you use, like particle swarm or basically neural network optimizer, which is a new one in the recent version of CMOST, actually will help you create diverse solutions with multiple combination of parameters, which will meet your acceptable history matching and optimization criteria. So the rate at which it converges to a solution, as well as so that it doesn't get stuck in the local optima. Different algorithms have different behavior. So there are some guidelines that we have published in our user manual, which will be helpful in deciding which optimization or history matching engine you should be using, and that will help you narrow it down pretty quickly. The next question is there any change in aquifer grids selection option for regional aquifer? Not pretty much getting that question, actually. You can define regional aquifers, and you can assign it to different local regions by specifying the region as grids or as sectors, and then you can actually parameterize that if there is an uncertainty in the assignment or location of the aquifer. The next question is, can you provide info on how to use the cloud to run the models? From 2017 version, we introduced cloud options. There are 3 different options, which is the CMG private cloud, where the computers are hosted by CMG here, and then there is the 2 public cloud options with Amazon AWS and Microsoft Azure. There are help manuals that will help guide you through the step-by-step process on setting up the cloud-based launcher. It's very simple with just few steps. I can actually send you a guide to how to set it up and activate the cloud option. I saw more than 360 cases in the history match, how long the total run takes, and how many CPUs cluster did you use? Yeah, it did take several runs, but if you look at, we let it run beyond a certain number of runs because we didn't want to limit it. But if you see, there are acceptable history matches within almost 50 runs as well. But if you look at the entire study, took only 1 hour 11 minutes to do it. So the runs are pretty fast, just running in few minutes. And the total study only took 1 hour, so we just let it run, and so that we get a complete solution and a global maxima rather than being stuck in a local optima. But if you do choose to stop it, you can see that within few runs you are able to achieve a very good history match. The next question is, do you ever get one unique optimization solution or a history match solution? Sometimes the chosen optimal may not physically make sense. The CMOST is all about trying the entire parameter space and coming up with acceptable solutions or equally probable solutions. And again, depending on the uncertainty ranges that you have, and depending on the duration of your history period. If it is only a few months of history, you don't have a lot of control points. So then, and if you have a lot of uncertainty in your parameters, you will end up with a various combination of equiprobable history matches that you can take into forecast. And that's why we are recommending to do a probability based forecasting, where you're taking all the acceptable history matches into a forecast and doing an uncertainty, creating your P10, P50, P90 forecasts, and so that you can cover the entire uncertainty range. And as you get more data to constrain your uncertainty, you can narrow down those uncertainty and narrow down your uncertainty in your forecast. So, but if you do choose to take a single solution into or a single solution for your history match, then you can narrow down your acceptable criteria and make it even tighter, so that only one or a few of those matched cases meet your acceptable criteria, and then you can take that one into the forecast. Just for the sake of time, I mean, I have so many questions here that I may not be able to take it today, but I do assure you that I will be following up with individuals in the next day or two, and we will be discussing each of these questions individually with each of the attendees. But again, thank you for attending today's webinar. We will be posting the presentation within the next 24 hours. Again, if you have questions about specifics on how to do certain things, we do offer a lot of training courses for all skill levels. You can check the CMGL website for training calendars and register for those training classes. If you have any questions regarding today's webinar or any other topic, please do not hesitate to contact us at sales@cmgl.ca, and we'll be more than happy to help you through the entire process. Again, thank you for joining us for today's webinar on CMG 101, Simulation Workflow Made Easy. And looking forward to seeing you in the next webinar, hopefully in the next 4 to 5 weeks. Thank you.